We're going to begin our first new material in trig regions class today and talking about solving absolute value equations and inequalities. Well, there is some new, but there's also a lot of old knowledge that you'll be able to bring to bear to get these things solved. So let's talk first briefly about what absolute value actually means. When you see absolute value, and you know that you see the two straight up and down lines like that, the absolute value of -5. Well, the absolute value of -5 really says how far is a -5 from the number 0. We go out on the number line, 1, 2, 3, 4. Oh, it's about this far. And that represents a distance. And when we talk about distances, we never talk about distances in terms of negatives. We just say, well, it's 5 hops to the left of 0, but it's 5 hops. If we were talking about a +5, and we took the absolute value of +5, we'd be out here somewhere. And guess what? That's the exact same distance. It goes in a different direction, but it's still a distance of 5 hops. So distance from 0 is what we're talking about when we're measuring absolute value. If we talk about the absolute value of x being equal to 3, well, where are we? Are we just in one place? We know that on the number line 3 is here. I'm going to reset 5. We know on the number line 3 is here. So we'd say, okay, if the absolute value of x is equal to 3, then it's 3 hops away from 0, so that must mean x is 3. And we put a dot there. But the question is there any other place on the number line where it's a distance of 3 away from 0? And as a matter of fact, if you go out to -3 on the number line, that's also a distance of 3 from 0. It's 3 hops from 0. So there are really 2 locations on that number line that represent the absolute value of x being equal to 3. So we've got a total of 2 answers there. Let's see what happens when we're dealing with inequalities. We just talked about an equation. We know for an equation we're going to have 2 different spots on the number line. So let's see about inequalities. Well, now we want to know, whoops, I meant to change this. This number should be a 3 right here. Now we want to know when the absolute value of x is greater than 3. In other words, where are distances bigger than 3 hops from 0? Well, 1, 2, 3 hops to the right. Now we don't want to know equal to 3. We want the distances to be greater than 3. And I think you'd agree that anything out here is going to be a distance bigger than 3. But just like when we're talking about the equations, we also go in this direction. 1, 2, 3 hops to the left of 0 is in fact 3 hops away, and anything out in this direction is going to be a distance from 0 that's bigger than 3. So we end up with a picture that looks like it's shaded on both ends of the number line. Last example on the number line here is, oops, another change I forgot to make. So we'll make that a 3 and that a 3. Now we're talking about absolute value being less than or equal to, in this case, less than or equal to 3. So we want distances that are smaller than 3 hops away. Well, distances smaller than 3 hops away, we have a different picture. We don't want to go distances larger than 3 hops. We want to go distances smaller than 3 hops. So certainly a distance of half is less than 3 hops away. A distance of 1 is less than 3 hops away. And we can color in all of these numbers, and as long as we stay somewhere in that green shading, we'll have a distance that's less than 3 hops away from 0. Likewise, we go to the other side. Certainly going in this direction, that's still less than 3 hops. We're still at less than 3 hops, and we want to stay at less than 3 hops so we can go almost touching 3, but we can't actually hit 3, and that's what an open circle represents. So there's another version of what an inequality might look like when we solve it. Okay, let's get to the actual solving. So much for the interpretation. When we solve these things, we're going to end up with the case of an equation. We don't have to worry about graphing on a number line. We're just going to solve. So let's look at a simple problem here. Let's pretend that we just have an x. Simple linear equation. What do? You clean up both sides. You start moving things around. You get 2x is equal to 30. And then you undo that multiplication. And we undo the multiplication here with a division. So we get an answer that says x is equal to 15. 15 is the only number that's going to work when you plug it in here. It's the only thing that'll give you a true statement. But take a look at how we went about solving that. And now I'm going to change this equation to an absolute value equation. Instead of the x that we had right here, we're going to put an absolute value expression in its place. So we're going to keep the 2, we're going to keep the plus 4, we're going to keep the equals 34. We're just going to change to having something with an absolute value expression. Well, we're really going to start this problem out the same way we started out the other one. You see, just like I wanted to get x by itself here, I want to get this whole absolute value yellow thing by itself here. So we're going to start out by subtracting 4 from both sides. We're going to do our move first. That'll leave me with 2 times absolute value of x plus 3 is equal to 34 minus 4 gives me 30. Notice the parallel between what happened on the left here and what's happening on the right here. What did I do here? Well, I wanted to get that x by itself. I undid the multiplication. Heck, I want to get this green absolute value by itself. So what am I going to do? I'm going to undo the multiplication again. Divide by 2. And now I have an absolute value that's all by itself. We call it isolated. X plus 3 is equal to 15. Still a lot like what happened here. So far we haven't seen any difference, except here we kept rewriting x until we got to this point. Here we're going to just keep writing absolute value of x plus 3 until we get to the point where it's all by itself. Here's where the interesting thing comes in. You remember that when we're solving equations, we had 2 green dots on that first example. So we need to come up with 2 answers out of this thing. If we pretend the lines aren't there, the only answer we'd come up with is a 12. So we can't just pretend the lines aren't there. What we're going to do is we're going to take each line and split it into its own equation. Well, that's going to end up giving us 2 equations. And if we have 2 equations to solve, we're going to end up with 2 answers. The first equation, the first line, we're just going to ignore the lines. We're going to write x plus 3 equals 15. That takes care of that first line, so you don't see any more lines in here. For the second line, we're going to write x plus 3 equals, and right here is where things are going to change a little bit. We're going to put a minus sign. We're going to negate the thing on the right for this problem here. Get my black pen back. Okay, so where did the little lines go? The lines turned into 2 separate equations. We don't need the lines anymore. I think you could all handle solving this, and you don't even need to write this at this point. Once you come up with x plus 3 equals 15, I think most you can handle coming up with x equals 12. And here we're going to subtract 3 from both sides. We're going to get x equals negative 18. There we've got 2 answers for our number line. You can double check both of them. You can plug each of them back into here. That's going to be 2 times 15 is 30 plus 4 is 34. A negative 18 would give me a negative 15 in here, but we'd be taking the absolute value. We'd get 30 plus 4 equals 34. Both of those numbers work. So we have 2 answers. And we don't need to graph those answers, but we certainly do want to consider checking, and you'll see why. Okay, so that's probably the hardest example that I could have given you in the absolute values. Let's do a couple of easy ones. I'm going to erase this. And let's look at some actually easier problems just because there's a little bit less work to do. In this problem right here, how would we start it out? Well, in this problem, the only thing we'd have to do before we start splitting is get rid of the 5 there. In this problem, there's nothing to do before we start splitting. This one's ready to split. And this last one also is ready to split. Let's take the middle problem and see what happens with the middle problem. We said it's ready to split, so let's show how we split it. X plus 3 equals negative 4. For the first line, I'll get x plus 3 equals negative 4. And the second line is going to turn into x plus 3 equals the opposite of a negative 4. Let's finish the solving here. Subtracting 3, x is negative 7. And x plus 3 here is equal to positive 4. 2 negatives make a positive. Subtract 3. I get x is equal to 1. Okay, that's great. This is what we were trying to solve. Let's go plug in and see what happens. Plug in a negative 7 here. Negative 7 plus 3 is negative 4. When I take the absolute value of a negative 4, I get a positive 4. My check is telling me that 4 equals negative 4. Uh-oh, that's not true. That negative 7 doesn't work. We're going to have to reject it. And now you're going to see why it's important to check these equations, because sometimes your algebra will give you a really nice answer that doesn't work. You have to reject that. Let's go check the other answer that we came up with. We got x equals 1. Plug in a 1 in here. 1 plus 3 is 4. Take the absolute value of 4, you get 4. And again, you got a statement that's 4 is equal to negative 4. Got to reject that one too. This thing has no solutions. Whoops, I shouldn't do that. It has no solutions represented either with a completely empty set of curly brackets, or you can also say no solutions by just drawing a 0 with a line through it. You can also say no solutions by writing out the words no solutions. So this is all about this problem number 2 here. We had the absolute value sign by itself. We split it up. We got 2 nice algebraic answers, but neither one of them work. We have to check it and we have to reject it. If you try this problem on your own, that one should work and you should get solutions for it. This problem should work. I'm actually not quite so sure, but certainly you want to get that absolute value sign by itself. And there's something interesting going on with this top one, so I want to show you that top one also. I'm going to erase this one. Okay, we're working on the top problem now. Get that box. And on that top problem, or I'll rewrite it for you, x plus 3 plus 5 equals 2x. So we want to get that absolute value by itself. Don't worry about what's going on over here. Let's just move the 5. It says absolute value of x plus 3 is equal to 2x minus 5 by itself, so it's time to split and get rid of the lines. For the first one, we're just going to write it without the lines. X plus 3 equals 2x minus 5. For the second one, we're going to write it without the lines. X plus 3 equals, but we are going to negate now the entire other side. So the entire other side means we're going to put that in parentheses and we're going to have to distribute that negative. And I would leave it up to you to go back and check in your notes. You can try to solve both of those, see the answers you get, and be sure to check them. We're going to move on to inequalities at this point. And inequalities, we're going to have 2 parts to an answer. Well, the good news is we don't have to check the inequalities. Okay, we're not going to give you ones that don't work out. But we will have to state our answer 2 ways, as an algebraic solution and as a graph. So we'll do that with the problems that we're going to tackle next. Okay, well, we'll start off very similar to the equations. For now, we're just going to pretend this is an equation. We're going to have to do the same thing we did before. We're going to have to get that absolute value part of it all by itself before we split. So, moving and undoing. We're going to have to move this 5. Subtract 5 from both sides. Now you've got 7 times your absolute value is equal to 19 minus 5 is 14. We want to get that green thing all alone. It's being multiplied by 7. We're going to undo that by dividing by 7 on both sides. And now my algebra leaves me with an absolute value 3x minus 7 is equal to 14 divided by 7 is 2. And now we're ready to split, but I did something here I should not have done. It's an easy fix. You see that less than sign? I, by mistake, turned it into an equals. So we're going to fix that. And so it's still going to be a less than sign when we get to here. Okay, it's time to split. Now splitting on an inequality is a lot like splitting an equation. We're going to take the one line and go this way. We're going to take the other line and go that way. We're going to write 3x minus 7 is less than 2. Just pretend the lines aren't there for the first one. When we get to the second one, we're going to write the 3x minus 7, but we're going to do 2 things. Instead of just negating the right-hand side, we're going to flip and negate. And that's the difference. When you're doing an inequality and you get to that second split, you will flip and negate. Other than that, we're going to continue with this, and we'll have a simple algebraic solution. Add 7 to both sides. 3x is less than 9. Divide by 3. X is less than 3. Circle that for now. Let's go to the other side. Same thing, we're going to add 7 to both sides. 3x is greater than, this is going to give me a 5 here. And we're going to divide both sides by 3. Holy moly, we got a fraction. X is greater than 5/3. Well, you know what? Fractions can be legitimate answers. There's nothing wrong with that. That's our algebraic solution. The inequality signs actually tell us how to set this graph up, so let's just go do it carefully. Put a 0 in the middle. We've got a 3 over here, or 0 in the middle, or kind of close to that. 5/3, well that's 1 2/3. 1 2/3, let's say if this is 1 and this is 2, we'll say 1 2/3 is, somewhere around here. And we'll call that 5/3. Now the blue answer says x is less than 3, so let's go to 3 and let's put an open circle and let's start shading to the left of it. Less than. The other one says x is greater than 5/3, so let's put a circle on 5/3. It's got to be open, and we'll start shading to the right. And they should meet. So any number that's in between 5/3 and 3, not including 5/3 and 3, but any number in between 5/3 and 3, if you pick any number and you plug it into this original problem, should work for you. And we'll try 2 really quickly. If you plug in a 2, I'll just do this in my head. It'll give me 6 minus 7, negative 1. Take the absolute value, it's 1 times 7. 7 plus 5 is 12, and in fact 12 is less than 19, so that does work. Okay, now this was a less than. With a less than, we're looking for small distances. But small distances means numbers that are kind of in between. Okay, if we have a greater than, we're going to be talking about very large distances, and you should be thinking of very large distances as going all the way off to infinity on this side and all the way off to negative infinity on that side. So let's see what one of those looks like, and then we'll be finishing up. Okay, we'll take a look at, oh goodness, a fraction there. Well, let's look at this one here. 2x minus 5 is greater than or equal to 3. Certainly you should be able to do the fraction on your own. 2x minus 5, ready for splitting. There's no cleanup to do. There's no moving around to do. There's no undoing to do. This thing is ready to be split. So let's split it. 2x minus 5 is greater than or equal to 3. That's easy enough. And then 2x minus 5 is less than or equal to, remember we got to flip and we got to negate. So it's going to be less than or equal to negative 3. Now you've got a couple of first year algebra problems to solve. They're not difficult. We're going to add 5 to both sides here. Gives me 2x greater than or equal to 8. We're going to divide by 2. Give me x greater than or equal to 4. Let's turn to the green one. Notice that the lines don't disappear until you split it, and now they're gone. Add 5 to both sides. 2x is less than or equal to, we're bringing down those signs. 5 minus 3 is 2. We're going to divide both sides by 2. X is less than or equal to 1. So here is the result of our algebra. And like I said, the inequalities you don't have to check. They should work out for you. Let's go to the number line. I got a 0 here. I've got a 1 here, a 2, and a 3, and a 4. We're going to use closed circles. This red answer tells me go to the 4, make a closed circle, and we want x's greater than, bigger than 4. We're going to shade in this direction, and we're going to put an arrow at the end of our shading. This one says x is less than or equal to 1. We'll go to 1. We'll put a closed dot. Less than means smaller than, so we're going to go in the left direction. And we're going to put an arrow on the end of our shading. And so what you see now is you see a graph that has a picture shaded on the ends. Now we're not just going to circle these answers because we want to state them as a solution set. And I missed that on the last problem. We'll pick that up in just a second. If I am looking at two separate parts of a number line, then I'm going to be making curly brackets. I'm going to be putting the word or in the middle. And I'm just going to rewrite these. X is greater than or equal to 4, or X is less than or equal to 1. So for two parts of the number line shaded on each end, you've got to, if they're separate parts, you're going to have to separate those statements with an or. But I want to just jump back and take a look. I'm going to move to the next screen. I'm going to take a look at what happens if we had it shaded in the middle, and I'll try to remember what numbers we were working with. We had a number line that was actually shaded in the middle of two numbers. I think it was a 0 here, and we had a 5/3 with an open circle, and we had a 3 with an open circle, and we were shaded here. Now we had a statement that said X is greater than 5/3. We had another statement that says X is less than 3. So when we see it shaded like this, we're going to write an and in the middle. And then we'll say X is greater than 5/3 and X is less than 3. So an and picture will be two circles with shading in between. An or picture will be two circles shading on the outsides, or multiple pieces of shading. This is only one piece of shading. I'm going to put the answers up for tonight's worksheet.